Okay, today we finished up our discussion of pipe flow and pipe networks, in fact. The theme here when we talk about flow in pipes is thinking about the head losses. And the total head losses are H sub L would be given by the major losses plus the minor losses. And the form each of these takes is the major losses have the form of the Darcy-Weisbach equation, F L over D V squared over 2G. And the minor losses are simply the summation of a loss coefficient times the velocity at the appropriate location squared on 2G. So they both involve this kinetic energy group, V squared over 2G, or if you write it in terms of Q, you'd have a Q squared over 2G and then a 1 over area squared factor. And in a way, you can think of this factor of L over D as a loss coefficient, and then there's definitely an analogy to be drawn there. I guess the main point, new point that was made today, besides just different types of problems that we frequently see in setting these problems up, is the idea of losses in series versus parallel. And the key thing in losses in series is that the losses are cumulative. That's what's assumed here, that we have a frictional loss, we have a series of minor losses that are just simply added up. For parallel networks, the losses have to be equal. So parallel branches, the losses are equal along each branch, are the same along each branch. That sets up an additional equation then that can be used to solve for how flow splits in a branching network. So let's say that we have a pipe network that consists of 3 pipes. So we have pipe A, pipe B, and pipe C. Then what this statement tells us is that the head loss along A has to be equal to the head loss along B, has to be equal to the head loss along C. That gives us 2 equations. You can think of the equivalency of head loss along A and B, or the equivalency of the head loss along B and C. So there's 2 equations. Now, if we're given a flow rate Q entering the system, then we have one other constraint on the flows, which is that the total flow rate Q has to be equal to the sum of the 3 individual flow rates, QA plus QB plus QC. So that gives us a third equation that describes the system. So here we have 3 equations, the blue, the green, the red, for the 3 unknowns, which are the velocities in each of the pipes, or equivalently, the volumetric flow rate in each of the pipes. And that allows you to define flow splits in a branching network.